Alright, so now in section 5.4 we're going to be looking at taking derivatives of exponential functions. The good news is that it's very, very simple. Alright, when we have an exponential function, we're going to look specifically at the natural base. So we said that the natural base of e was approximately 2.72. I wanted to remind us of something before we get started with actually taking derivatives, something that's going to help us out along the way. Anytime we take a positive base, and that's all we have, anytime we take a positive base, let's say 2, we raise it to a positive power, we always get something that is positive. And in fact, we say something is positive by saying that it is always greater than 0. So if I take a base, a positive base, and I raise it to a power, I'm guaranteed that it's always going to be greater than 0. So this is going to be a helpful tip that we're going to see later on along the way. Okay, so we'll just keep that in mind. So here we have the base of e, which we said was approximately 2.72, and we're raising it to the x power. And what we want to look at is taking the derivative with respect to x. We want to take the derivative of that natural base. It turns out that the derivative of e to the x is e to the x, so it looks exactly the same. So that's really nice. So it does get a little bit more interesting, so let's look at that. What if we have something other than x as the exponent on that exponential function? So let's say that we have e, and let's say we have something else, and that something else is actually kind of like an inside function. So we have something like the chain rule for our exponential functions. So we're going to have e to that power, and then we're going to multiply that by the derivative of that power. Okay, so it's kind of like the chain rule. We have kind of like the inside function that we keep as is, but then we're going to multiply by the derivative of that inside function. So if I write this out in words, if I'm taking e, the derivative of e to some power, okay, then we're going to write down e to that power, just going to write down exactly that, sort of like the first rule, except the only difference is if you have something other than x in that power, you're going to multiply then by the derivative of that power. Okay, so that's what it is out in words. Okay, so overall it turns out to be a pretty easy thing to take a derivative of. Okay, so for example, if we have f of x equals 3 times e to the x, if I want to take the derivative of this, okay, any constants that are being multiplied times e, we can just bring them on down. And then we want to take the derivative just of the part that contains the variable, so e to the x. Well, what's the derivative of e to the x? Well, that's just e to the x. So it turns out the derivative of that is exactly the same as the original function. All right, what about our next example? This time we have something other than just x as the power on e. So when we take the derivative, okay, the first part is really easy. We're going to copy down exactly what we see. So we're going to write down e to the negative 2x power. So we always copy down first e to that power, exactly as we see it. Okay, so that doesn't change. The only thing now that we're going to do is we're going to now multiply by the derivative of that power. So negative 2x, what is the derivative of that? Okay, well we know that the derivative of that would be negative 2. So our first derivative turns out to be e. Sorry, let's simplify a little bit. Let's bring the negative 2 to the front, that constant, so that's negative 2 times e to the negative 2x power. Alright, so a pretty easy rule. You copy down exactly what you see first. If you have e to some power, you copy that exactly down, and then all you do now as an extra step is to multiply by the derivative of that exponent. Alright, so the next example, we're going to take a derivative. We're going to do it term by term, so we're going to focus on this first term here. We have a constant times e to the x. We're going to bring the constant down, and we're going to focus on taking just the derivative of this part of the term. Well, we know that the derivative of e to the x is just e to the x. Nothing extra, that's it. Now what about the next term? Well, the next term doesn't have e in it at all. In fact, this is something that we would have talked about way back a long time ago in chapter 3. Well, what's the derivative of minus x squared? Well, that's just negative 2x. So we have a mixture there of exponential terms with polynomial terms that we talked about at the very beginning of the semester. All right. So here we have f of u equals u squared times e to the negative u power. All right, so we have u to the u squared times e to the negative u power. So one thing we want to keep in mind is that the variable that's used throughout the function is u. And u is the same thing basically as x. It's just a variable that's being used as the variable of the function. So we have a variable u and a variable u in the two separate factors of this product. So to me, this sounds a whole lot like a product rule. It smells like a product rule. All right, so not two C's, but one. Product rule. So we're going to take the derivative here. We're going to do first times the derivative of the second plus the second times the derivative of the first. So f prime of u. So the first, we're going to focus on u squared as the first. So we're going to write down the first as is times the derivative of the second. Okay, so that's e to the negative u. So that's not just e to the x power or e to the u power, that's e to the negative u power. So it has a power other than just u or x. So the derivative of that would be copied down exactly as we see e to the negative u power. Remember, that's the first step. But the next step in taking that derivative would be to multiply by the derivative of that exponent. Well, the derivative of negative u would just be negative 1. All right, so there's the derivative of the second. Okay, now we're going to add to that the second as is. So we have e to the negative u power. And then we're supposed to multiply that by the derivative of the first. The derivative of first is pretty easy. It's u squared, so the derivative of that would just be 2u. All right, you can leave that exactly as is, or you can do a little bit of simplification. Probably the most that we're going to be able to do is just bring the constants to the front. So if I bring a negative 1 to the front, I'm going to write that as negative u squared times e to the negative u power. I'm going to bring this to the front as well of this term. So this separate term, I'm going to write 2u times e to the negative u power. So you can leave it as is, or you can do a little simplification. Just be careful when you simplify. All right, so our next example, we have x as the variable for the function. So we're going to be aware of that. We're going to take the first derivative here. And since we have a variable on the top and a variable in the denominator, this is going to be, we're going to practice here our quotient rule. Okay, so the quotient rule says denominator, as is, times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So, denominator, e to the x, times the derivative of the numerator. Well, what's the derivative of x? That's just 1. Minus the numerator, as is, so that's x, times the derivative of the denominator. Well, what's the derivative of e to the x? Well, since that's just e to the x, then we know that the derivative of that was also just e to the x. Then we're going to divide by the denominator squared, so we have e to the x, and then we're going to square that. All right, so a little bit of simplification here. I'm going to multiply. I have e to the x times 1, that's just e to the x, minus x times e to the x, all of that over. Remember, when we raise a power to a power, what can we do with the exponents? We can multiply them. So I get e, and then I get x times 2, well that's 2x, so our power becomes 2x. Okay, you can leave it like this, or you can do a little simplification. And once again, just be careful if you do decide to simplify. All right, example 6 is also the quotient rule. We have a fraction and we have a variable of x in the numerator and denominator. So the variable of the function is in both locations. So we'll definitely be employing the quotient rule here. So first derivative, it's going to be the denominator as is. Now this is two terms, so you want to be careful to put parentheses around that. So there's the denominator, times the derivative of the numerator. Well, we know the derivative of e to the x is just e to the x again, okay, minus the numerator, as is, times the derivative of the denominator. So let's look at our denominator here. Okay, we're going to do it term by term. The derivative of e to the x, well, that's just e to the x. What's the derivative of 1? Well, that's a constant, so we know that's 0, so our derivative of the denominator is just e to the x. Of course, then we're going to divide all of that by the denominator squared. So e to the x power plus 1. We're going to take those two terms and we're going to raise them to the power of 2. All right, so if you chose to simplify a little bit, you can do that. F prime of x is equal to, we can do a little distribution there. Okay, so we want to think about something. When we multiply like bases, what do we do with our exponents? And let's just review that rule. So let's say I have 2 to the 5th times 2 to the 3rd. If I multiply with like bases, don't we add the exponents? So we end up with 2 to the 8th. Okay, so here that's what we're doing. We're multiplying like bases. We have e and e. Okay, e and e. What do I do with the exponents? Well, I'm going to add them. So what I have then is e, and then I have x plus x. Well, what is that? X plus x, that's 2x. So we get e to the 2x power. Okay, plus e to the x times 1, well, that's just e to the x, minus, okay, so we're going to multiply again, so I'm multiplying like bases. I'm going to add the exponent. So I get e, I'm going to add x plus x, that gives me 2x, all over e to the x plus 1 squared. Let's simplify just a little bit more. We have e to the 2x and we have minus e to the 2x, and those are going to cancel out. So we're left with e to the x divided by e to the x plus 1, all of that squared. Okay, so you can leave it like this, or a little bit of simplification gets us to something a little bit nicer. All right, in example 7, we're asked to find a second derivative of this function. All right, so we're going to work term by term here, and we have to find the first derivative first. So we're going to work term by term, so we're going to look at this term here. So we have a constant that's being multiplied times the front, so we're just going to bring that constant down, and we're going to focus on the part that has the variable. And the variable of the function is t. So what is the derivative of that? Remember that anytime we have e to some power, the first thing we're going to do is we're going to directly copy down e to that power. Okay. The second step that we're going to do is we're going to look at that power, and I'm going to say, what is the derivative of negative 2t? Well, the derivative of that would be negative 2. All right, so now we're going to move on to the next part. So the next term is negative 5 times e to the negative t. So first of all, we're just going to copy down that constant of negative 5. Now we're going to take the derivative of the part that has the variable in it. So e to the negative t. Remember, when we have e to some power, the first thing we're going to do is we're going to copy down exactly e to that power. Then we're going to multiply by the derivative of that power. So what is the derivative of negative t? Well, that's negative 1. Since we are taking a second derivative, we definitely would like to clean this up a little bit so that our second derivative will be a lot easier to find. So we're going to multiply together within this term. I get negative 6e to the negative 2t power. And then within this term, I have negative 1 times negative 5. I get positive 5, and then e to the negative t power. All right, so now we're going to find the second derivative. Okay, it's just a little bit more of the same. So we're going to bring down the constant for the first term, and then we're going to focus on the part that has the variable in it. So we're going to bring down e to that power. So we're going to copy that first down exactly as is, and then we're going to multiply by the derivative of negative 2t. The derivative of that power, once again, is negative 2. Okay, just a lot of more of the same. For the second one, we're going to bring down the constant as is, and then we're going to focus on the part that has the variable, e to the negative t power. We're going to copy down e to that power exactly as is, and then we're going to multiply by the derivative of that power. So we get negative 1 again. Now, look at the part that's in orange above. When we found the first derivative, that's exactly the same. And it's going to be the same every single time that we simplify and take a derivative again. It's going to be the same thing. So let's just clean this up a little bit. Now within this term, I can multiply everything together. I get a positive 12 and then e to the negative 2t power. And then within this term, I get negative 5 and then e to the negative t power. So that is our second derivative. So if you can take a first derivative, second derivative is just as easy. Okay. In example 8, we're asked to do something a little bit different than what we've done in this section, but a lot like what we did in section 4.1. We're asked to find the intervals for where this function is increasing and where it is decreasing. So in order to find increasing and decreasing intervals, what do I need? First derivative, second derivative, what do I need? Well, to find out where something is increasing or decreasing, I always need to find the first derivative. So let's do that. So I'm going to find the first derivative of the function. So what we have is e to this power. So let's rewrite this power a little bit so it looks a little bit more friendly. What we have is negative x squared divided by 2. This is the same thing as writing a power of, when I divide by 2, that's the same thing as multiplying by the reciprocal. So I'm going to write this as negative 1/2, since we have the negative out front, negative 1/2 times x squared. Alright, so these two are the same thing. This is a little bit nicer when we go to take the derivative of that power. Alright, so let's take the derivative now. So you have e to some power. We're going to copy down exactly as is, e to that power. And then we're going to multiply by the derivative of that power. So what is the derivative of negative 1/2 times x squared? Well, we're going to multiply 2 times negative 1/2. So I get negative 1. And then we're going to reduce the power on x by 1. So we get negative x. Let's simplify that just a little bit. Negative 1x is just negative x. Okay, and then we have e to the negative 1/2 power times x squared there. Okay, remember all of this is in the exponent for e. Alright, so what's the next step for finding increasing and decreasing intervals? Well, we want to take that first derivative, remember, and set it equal to 0. Or we want to find out where it's undefined. So we'll talk about that a little bit more in just a second. First of all, let's find out where the first derivative equals 0. So let's do negative x times e to the negative 1/2 x squared power. We're going to set that whole thing equal to 0. Now we have two things multiplied together that is equal to 0. So I'm going to set the first factor equal to 0, and I'm going to set the second factor equal to 0. Alright, so negative x equals 0, well, that simplifies basically just to be x equals 0. And then here we have a positive base e raised to some power. Remember what we talked about a few minutes ago at the very beginning. Anytime I have a positive base raised to any power at all, it doesn't matter if there's a negative there or not, a positive base raised to a positive power is always going to be greater than 0. Okay? The only way that I can get exactly 0 is if the base was 0 itself, because 0 raised to any power would give me 0. In this case, we have e. E is definitely not 0, it's 2.72. So there is no way that you're going to be able to take the base of e, raise it to any power, it doesn't matter what that power is, and get 0. So there's actually no solution for the second part. So that's completely impossible. E to any power at all, doesn't matter what that power is, negative, it looks kind of crazy, it doesn't matter. We're never going to get 0 from that. So if you were thinking, well, what about where the first derivative is undefined? Okay, because there is a negative exponent, you might say, well, let's rewrite it. That would be negative x over e to the positive now 1/2 power x squared. Well, it doesn't matter if we move that to the bottom and give that a positive exponent. This is still not going to equal 0. So there is no place where our denominator now would equal 0, so there is no solution for that as well. So all we have is x equals 0 to separate as a separation value for our number line. Alright, so we want to find out where we're increasing and decreasing, so we're going to take the first derivative and we're going to plug in some test values. So from the left side, I'm going to choose negative 1, and on the right side, I'm going to choose positive 1. And remember, we're plugging them into the first derivative. We want to know what is the slope. So we plug in negative 1. I am going to plug that into our first derivative here. Alright, so f of negative 1. So everywhere we have an x, we're going to put some parentheses, and then we'll put our negative 1 inside. Negative times a negative, we get a positive 1. And let's think about this for a second. All we want to know about is this going to turn out to be positive or negative? So let's think about this. All of this combined, it really doesn't matter what the exponent is. E raised to that exponent power is always going to be something positive. So I really don't even care what that value turns out to be because I know it has to always be greater than 0. It has to be positive. So 1 times positive. Positive number there. So positive times a positive, we end up with a positive. And if we have a positive slope, then we know that the function is increasing for that interval. Now, if you don't believe me here with this exponent e to that power, you can always get your calculator and say e to that power, and you can plug in that exponent. What would that turn out to be? Negative 1 squared would be 1, so you can plug it and raise it to the negative 1/2 power. If you don't believe me, you can put that into your calculator, and you will see that you will get something positive every single time, regardless of what the sign of the exponent is. All right, so I'll leave that to you. F of positive 1, so let's put that into our function. So I'm going to put parentheses everywhere I have an x, so negative parentheses times e to this exponent. And remember, once again, it doesn't matter what that exponent turns out to be, so I'm not going to even plug it in for this part. We know that this will always be something positive. So I'll put the 1 here. We get negative 1 times e to that power. So a negative number times a positive number, we're going to get something negative. And we know that if we're negative, we have a negative slope, that the function is decreasing for that particular interval. All right. So our question was, where are we increasing, where are we decreasing? So we'll kind of scoot down just a little bit. Let me zoom out just a tad so we can have a little more room. So where's the function increasing? Well, it's increasing from negative infinity to 0. Where is it decreasing? It's decreasing from 0 to positive infinity. And the last question we had, well, actually we don't have that question, but we could ask ourselves, well, is 0 a relative max or a relative minimum? And because we go high and then we come back low, this would turn out to be a relative max. Okay, we weren't asked that question, so we'll just stop there, but we could go a little further if we so chose. Okay, we have a couple of word problems here. So a lot of applications involve exponential functions. So for example 9, we have the average energy consumption of the typical refrigerator freezer that is manufactured by this particular company is given by the function c of t equals, and then we have all of those terms there. And it's on a little bounded interval there from 0 to 20. And it tells us some information about that function. It says that this gives us output in kilowatt hours per year. It says that t is measured in years, and t equals 0 corresponds with 1972. Okay, so it has some information there. It says, what was the average energy consumption of the freezer at the beginning of 1972? So this was not asking me for a rate of change, it's just directly asking me for a number corresponding to this function. So that's what the function does. It tells me kilowatt hours per year. So it tells me the average energy consumption. So we're going to take our value that represents 1972 and we're just going to plug it into the function. So c of 0 equals, and we're just going to plug this value in to the function in place of t. Okay, it's right up here in the exponent. It's kind of small, but it is there. Okay, so let's look at this part first, and you could throw that in your calculator if you want to, but it's a little bit easier than that, because when we take any number, we multiply it by 0, we know we get e to the 0, and we know that e to the 0 is 1. So we have 1360 times 1, okay, plus 500. Well, that's pretty easy. 1360 times 1 is 1360, so all I have to do now is add 500. So it turns out to be 1860 kilowatt hours per year. That was the average energy consumption of a refrigerator freezer in 1972. All right. Here in part B, we're asked to prove that the average energy consumption is decreasing over the years in question. So are they decreasing in the years where t equals 0 to t equals 20? So the years in question would be 1972 when t equals 0, and then 20 years later, 1992. All right, so let's prove that we have a decreasing function over that particular interval. So in order to prove that, we want to take the derivative to work with increasing and decreasing functions. So when we look at the original function, we have a constant times e to some power. So we're going to bring the constant down, and then we're going to focus on the part that has the variable. Okay. Remember, if it's e to some power, we're going to write e to that power exactly as is first. So pretty easy to do that. And then we're going to multiply by the derivative of that exponent. Also pretty easy. It's just the number that's in front of t. Now, the second term is just a constant, plus 500. So the derivative of that is 0. So we have the derivative right here in front of us. So we are done. Let's simplify it a little bit because we are asked to prove something. We're going to use it to prove that it's decreasing. So what we're going to do is we're going to multiply the constants together within this term. So we're going to multiply 1360 times negative 0.69. Okay, just throw that in your calculator, and when you do, you get approximately about 93.84. And we're going to bring down the e to that power again. Okay. Now, the nice thing is that this is actually a really easy question to answer. Why is that? Well, let's look at something here. This right here, remember, is always something positive. So it doesn't matter what value we plug in for t. It does not matter. That is always positive. That's not going to change no matter what. This value here is always negative. So we have a negative times a positive. So what do we know from 0 to 20 from that particular interval? Okay, let's pick a little number lines from 0 to 20. What's happening to the function? Well, if the function is always, that derivative, in other words, if that derivative is always negative, then what do we know? Well, if the derivative is negative, that tells us that the slope is negative, so it tells us that we are decreasing. And this would be true for any value that you would pick for t, so it doesn't matter what point in the number line that you would pick, the function is always decreasing for any t value. So it's decreasing for the entire function. So we have just proven here that the average energy consumption is decreasing from t equals 0 to t equals 20, so it's decreasing from 1972 to 1992. All right, part C says here, all refrigerator freezers as of 1990 must meet the 950 kilowatt hour maximum energy consumption set by this particular act. We want to show that the refrigerator freezer satisfies this requirement. We want to compute the average energy consumption at the beginning of 1990. So when is 1990? If t equals 0 corresponds to 1972, then 1990 would be 18 years later, so we're looking at a t value of 18. So let's prove that in that year, the energy consumption was below 950. So I'm going to plug 18 into our c function there. I get 1360 times e to the negative 0.069 power, and our t value is going to go right into the parentheses there, so it's going to be times 18, and then on the outside of that we're adding 500. Alright, now all you have to do is throw that directly into your calculator. One thing that you want to be careful about is that when you have the e to that power, make sure that you put all of this in parentheses, okay? Make sure that all of that is in the parentheses and all of that is in the exponent. Usually in your calculator you end up seeing something like this, E2, and it gives you the first parentheses. You're going to plug all of that in exactly as you see it, times 18, and then make sure you close out the parentheses before you add the 500. Okay, also on your calculator, you might have to hit the second button. Usually you have to hit the second button that's somewhere on the top left of your calculator usually. Sometimes you have to hit the second button and then hit the button that says natural log or ln, and the e to the x should be right above that button. Okay, so if you're having trouble putting that into your calculator, consider looking for that second button, hitting ln and making sure you have that, and then everything else should be pretty straightforward. One last little helpful tip about your calculator. This negative right here, usually you're entering in not a subtraction symbol, but you're entering in, you have a little button at the bottom of your calculator. It looks like a parentheses with a negative inside. This is what you input when you're not talking about subtraction, but you're talking about a negative number. Okay, so just be careful about that. Now when I plug that into my calculator, I get 892 point, we'll round to the nearest 3 decimal places. I get 892.776, and this is the kilowatt hours per year. Oh, so have we met a requirement? And it looks like we have. The maximum was 1950, and we are below 900, so it looks like we definitely meet the requirements of that particular act on the refrigerator freezer energy consumption. In our last example for this section, we have here that the total number of units of a new product sold T months after its introduction, so T stands for months after introduction of this product, is given by the following function. And we have our bounds for T is 0 to 36, and we're asked to round to the nearest integer, so we'll keep that in mind. It says how many units of the product were sold 17 months after its introduction. Alright, so this is not asking me for a rate of change or how fast something was happening. This is just how many units. Basically, we're just going to plug into the original function. So I have n, and I'm going to plug in 17, and we're going to put this directly in place of t. Alright. So I put a 17 in place of t, and this involves a little bit of calculator work. So I'm going to write down kind of an example of what I would put into my calculator. You're going to type in 20,000, and you're going to hit times, and then you're going to start your parentheses. You're going to do 1 minus e, and you'll see the little caret symbol that looks like a little roof of a house, e. And you're going to type in that negative button. Remember we talked about that negative button on your calculator. It looks like at the bottom right, you should have a little negative symbol with parentheses around it. This one right here is actually the subtraction because we are actually doing a subtraction. This one will be that negative symbol. So negative, you'll type in 0.05. You're going to multiply by 17 and make sure that you close the parentheses to say that's where the exponent stops. Now we need one more parentheses here, and then we're going to raise all of that to the power of 2. Okay, we need this parentheses here, and we need this parentheses here. These two go together so that all of this in the parentheses, we know all of that, the entire quantity is going to be raised to the power of 2. Okay, so you should end up getting 6,557 units when we round to the nearest integer. All right, so the next question asks us a how fast question. So it's saying how fast, and that's a rate of change. And if we remember rate of change and how fast, those questions are dealing with the derivative. So derivative is rate of change. So we're going to find the derivative of our function. All right. So what we have here is 20,000, which is a constant, times a group of terms all raised to a higher power. So that sounds a lot like the chain rule. Okay, so we're going to use the chain rule here to solve the problem. So we have a group of terms raised to a higher power. We're going to multiply that power times the front of the function. So we end up with 40,000. We're going to write the inside function as is. Reduce the power on that group by 1. Then we have to multiply by the derivative of the inside function. So what is the derivative of the inside? All right, so we have two terms. The derivative of 1 is 0. So let's focus on the part that has the variable in it. So we have negative, this is like a negative 1. So we're going to copy down the constant. And then we have e to this power. So remember, we're going to copy down exactly what we see, e to that power. And then we're going to multiply by the derivative of that power. So the derivative of negative 0.05t would be negative 0.05. Okay. All right, I'm not going to do too much simplification here. Let me erase a little bit of our lines. Let's make it look a little nicer. Okay, so I'm not going to do too much simplification here. We'll do a little. So essentially we have negative 1 times e to this power times this negative 0.05. So let's take the constants that are all being multiplied in, and let's just multiply all of those together to make it look a little nicer. So n prime of t. 40,000 times negative 1 times negative 0.05. Put that into your calculator, you get negative 2,000. So kind of grouping all of those together. I have this term here, so I'm going to write, or this parentheses here, I'm going to write negative 1 minus e to the negative 0.05 times t power. And then we have this left over here. So we have times e to the negative 0.05 t. Okay. Well, I think I'm going to leave it just like that. I'm not going to do too much more simplification. Okay, so what was our question? We want to know how fast the product was selling 17 months after its introduction. So once we have the derivative, we're going to plug in 17 into the derivative. Okay, we want to know the rate of change at 17. So I'm going to put 17 in the exponent there. And we're going to put 17 in place of t in the exponent here as well. Okay, I think I have too many dots. Take that one. Right. I think I lost... Nope, I didn't. We're good. Okay. So we're going to put all of that into our calculator, kind of using the techniques that we talked about in part A there, making sure that you type it in correctly. Okay, shouldn't be too bad. Once we multiply all of that together, you should get 489 when you round to the nearest integer. So it's growing by 489 units. So we want to know how fast. 489 units looks like it's increasing by that many units per month.